people a couple more minutes to trickle in the meantime, these QR codes on the right can take you to either nominate yourself or a colleague to give a talk. We're taking nominations for next year's, the 2025-2026 year series, as well as the second QR code. You can go see the schedule and access the previous recordings that we already have. All right, Emil, why don't you go ahead and take over the screen share so we can get started in the next minute or so.
Okay.
All right, perfect. All right, so thank you everybody for joining for this month's DGRAV seminar. We have one more coming up in May, and then we'll take a break for the summer, and then we'll kick it off again in the fall. So reminder to nominate yourself or a colleague if you either want to give a talk yourself or you've seen some exciting work that you'd be interested in hearing more about. So in the email announcements that you've gotten, and I assume you're getting them and that's why you're here, you should be able to access a link to be able to nominate speakers. So yeah, thank you everybody for being here. Reminder that as a DGRAV APS sponsored event, you agree to adhere to the code of conduct. So everybody please be respectful and kind as we listen to Emil and Evan give us their presentation, starting off with Emil. So go ahead, take it away. Oh, wait, sorry, one more clarification. Questions are preferably saved until the end of both talks, but feel free to ask clarifying questions that are necessary for the talk to be able to continue during the talk, and or post them in the chat, and then we'll get to them at the end of the talks. Okay, now Emil, go ahead and take over.
Thank you, Deborah. Can everyone hear me? Yep. Okay. All right. So what I'm going to be talking about is basically two things intertwined together. One is gravitational vacuum condensate stars, which is an idea that was proposed some time ago with Pablo Mazur, and there are some earlier references there. And as I'll show, that idea even is inherent even in Schwarzschild's second paper in 1916. So that's quite a nice and interesting throwback into the history. And the new developments are that in an effective theory of gravity, which I will describe, or at least outline, which is based on these more recent papers in 2022 and this one on the archive, which will soon appear in PhysRevD. Basically, all of this can be put onto a Lagrangian basis. One can show that there are corrections to general relativity, which are then important for black holes or non-black holes, and can lead to a non-singular object, which is free of information paradox and the various issues plaguing classical black holes. So with that, I'll try to just outline the motivation, and you're probably all familiar with classical singularity theorems, which convinced most people long ago that there are such things as black holes, really black holes. We know there are compact objects. We have images from the Event Horizon Telescope, but none of this really tells us what's happening right at the event horizon or inside. So the full mathematics of general relativity and the black hole solutions that we're familiar with really depend on energy conditions that they could form from actual matter. So as probably all know, Penrose pioneered this in 1965 by imposing or demanding the null or weak energy condition that the energy density plus any of the pressures in any of the three directions, if you diagonalize the stress tensor matrix, if all of those are greater than or equal to zero, and very importantly, and a trapped surface is present, then you will basically be focused down to a singularity, and a black hole as we know it in classical GR will have to be the result. Alternatively, Hawking and Penrose in 1970 uh, uh, did away with the condition of a trap surface, but at the expense of making the energy condition stronger, and that leads to the strong energy condition, which is the sum of all of these pressures has to be plus the energy density greater than or equal to zero. Now, all of this seems very reasonable for classical matter, but it's also violated, we know, even in hadronic physics and the bag constant of nuclear physics. But you're probably more familiar with the dark energy that's present in our universe according to the supernova data, or inflationary models all require an effective cosmological term in which the pressures are equal and equal to minus the energy density, which is positive. And so that means that this condition no longer holds. So what's the relevance of this to black holes is that if you have negative pressures, then you have defocusing of geodesics, and that acts as an effect of repulsion, which you're familiar with from the fact that the inflation and the dark energy are effectively causing the universe to expand even faster, to accelerate. So that's kind of a repulsion. Okay, so the setup we're going to be discussing here is not inflation. It's static and spherical symmetry to make things as simple as possible. And in that case, you can easily show that there are two metric functions that you need to determine the line element, which is a function f of r, which is the TT component, and a function 1 over h, which I introduced for the radial component. And you can also write h as in terms of a mass function, m of r, the Misner-Sharp mass. So you have two metric functions, and if you demand spherical symmetry, then you have at most three different stress tensor functions along the diagonal, which is the energy density, the radial pressure, which I don't give an index, and the transverse pressures, which can be different in principle in a spherically symmetric situation. So you have 5 functions in all to determine. You have 2 Einstein equations, which are written here, and you have one conservation or pressure balance equation, which is this one. So you have 3 equations with 5 unknowns. It's obviously undetermined until you give further information, typically imposing isotropic conditions on the pressure and give some equation of state. But that's not what we're going to do. We're going to review, first of all, what Schwarzschild did way back in 1916. So everyone knows the exterior Schwarzschild solution, which I won't go over again. But Schwarzschild was interested in solving Einstein's equations also for the interior of a star. Of course, at that time, he wasn't thinking about black holes. He was thinking of stars. So he supplied the 2 additional conditions in the form of isotropic pressure. So P perp is equal to P. That eliminates one of the 5 functions. And he also assumed, for simplicity, basically, that the energy density in the interior of the object is a constant, which is just its mass divided by its volume, where R is the total size. And of course, he was thinking of things much bigger than black holes. Well, then you can solve the equations. You find the mass function goes like this, H goes like this, and I introduced this parameter capital H, which is this ratio of basically the Schwarzschild radius to the cube of the size of the object. And the only equation you have to solve then is the pressure equation. and you get this answer, which this is in various books, so you can look that up. Okay, so nobody really looked at this much further because you can easily see that this denominator will vanish, and therefore the pressure will become infinite, divergent, at a certain radius r naught, if the size of the object, the radius of the star, let's call it, is less than 9/8 the Schwarzschild radius. This is called the Buchdahl bound, if you know about that. So it was believed for a long time that there was no point looking at this any further because, well, it would only get singular. However, there's a very interesting observation that you can make about this. Namely, if you ignore that and just nevertheless take the radius to be equal to the Schwarzschild radius, then this h squared times r squared is equal to 1. And so this the square root vanishes, as does this one, and then the ratio is -1. So you end up with a p equals minus rho interior, which is a cosmological-like term, and with a negative pressure. So it can exactly do the job of being a non-singular interior solution. So here's just a graph of that. I won't go through all the details, the intermediate steps, but the bottom line is that if you take that limit of Schwarzschild's solution, it's inherent in his 1916 paper, although he didn't do that limit. Mazur and I looked at it in 2015. The pressure becomes equal to minus the density, which was constant, so the pressure is constant. And there's no more divergence in the interior at all. However, there is a discontinuity in the derivatives of the metric functions. So here's the square root of f. In the interior, it looks like this, which is de Sitter-like, and the exterior, it's Schwarzschild-like, and so the derivatives are discontinuous there. So you have to understand what that means, and that is not hard to understand. You can look at this piecewise continuous set of functions. F of r and h of r are given by this. Notice there's a curious 1/4 here, which is actually important because it will end up making, as I'll show in the next slide, the surface gravities equal and opposite on either side. I'll mention that in the next slide. In any case, if you have these metric functions, take this as a solution of Einstein's equations with an effective cosmological term inside, which is just 3 over the Schwarzschild radius squared. I'm changing notation here, so sorry about that. The Schwarzschild radius I was calling RS, I'm now going to call RM to indicate its dependence on M, so it's the traditional Schwarzschild radius. And you now look at this thing by more modern techniques, and you can see that this discontinuity actually means a surface tension and a physical surface at this point, at the would-be horizon. So here's the little bit of mathematics you have to know. There's a step function discontinuity in the surface gravity, which in these coordinates is just written this way. And you see that's where the factor of 1/4 in f is important. And so the surface gravity is this, minus 1/2 rm as I approach rm from the interior, from the de Sitter side, but it's plus 1/2 rm as I approach from the outer side, the Schwarzschild side. And it's important that these are equal and opposite because basically you have an equal and opposite force on the membrane, if you want to call it that, at this point. Okay, so basically things are being accelerated outward, pushed outward by the repulsive effect of the cosmological term, but pulled inward on the outside from the normal attractive force of gravity. And this can be analyzed and shown to this discontinuity is actually a surface tension, which you can check through Einstein's equations themselves. If you keep track of the step function and its derivative, you'll get a delta function exactly at the Schwarzschild radius in the angular components in theta and phi. The interior is non-singular, so needless to say, it's not an analytic continuation of the Schwarzschild exterior, as you usually do in classical GR. And you can work out what the first law means here, namely just the energy balance equations. And you find that the surface energy is indeed proportional to the change in surface energy is proportional to the change in the surface area, and the proportionality constant is just exactly this surface tension. So, this is a formula in relativity, in classical relativity. Notice there's no H bars here. That would be recognizable to Rayleigh if you've studied soap bubbles or bubbles in any liquid. There's no temperature here. There's no entropy. It's simply a mechanical relation with the surface tension and the area in energy balance. All of this is in this 2015 paper. So this is where we start as, if you wish, a classical model for Gravistar. And we now want to understand, can this actually be derived? Okay, can we actually, because of course I've shown you that you have to have some kind of surface tension here, but I haven't shown you where that comes from. It simply comes from the discontinuity of the metric functions, but I haven't given you a first principles derivation of where the stress tensor comes from. So that's what I'm about to discuss in this effective theory, which is the new development in all this. All right, so switching gears here now, we're going to come back to this solution at the end, but now I want to take this big parentheses basically to explain a little bit of what goes into this effective theory, which is going to describe the origin of this membrane and this stress tensor at the horizon. So the first thing you have to know about is the conformal anomaly, which I won't have time much to go through in detail, but there are a number of papers which are referred to, which can show you that the conformal anomaly, and in fact, the effective action that corresponds to the conformal anomaly, is relevant for macroscopic effects in gravity, in particular on horizons. So this is a generalization, actually, of what is known about chiral anomalies in, for example, QCD, but now the application to gravity. So that's the first important new element, and this is going to add a new degree of freedom, a scalar, called a conformalon, into the low energy gravity, into the effective action and the stress tensor that you get from quantum effects. Of course, we're going to keep GR as the base, the first term, the most important term. Oops. Let's go back there. The second big element, the second change from just standard GR, is that I have to describe the vacuum energy differently than just a constant, right? If it were just a constant everywhere, there's no way I could get it to change from inside to out. And actually, independently of this application, there's good reason to think that it should be replaced by something that can actually be adjusted according to boundary conditions rather than a fixed constant of Lagrangian. And it's known for years, I think, in some areas, like in supersymmetry and string theory, that lambda can be replaced by a four-form gauge field, an abelian field, and then becomes an integration constant. I'll show that in the next couple of slides. So we're going to replace the fixed constant of GR by an effective term, which is a constant if you don't have any important quantum effects going on. So it's equivalent, actually, to a fixed constant in GR. But it takes a different role, and it's not fixed once it's coupled to the anomaly. And that's what I'm going to describe. The reason to do this independently of this application is that this decouples the UV divergences or Planck scale physics that people usually say, the value of lambda is unnatural and so on. You don't have that problem if you replace it by a four-form gauge field. And then there's a free integration concept, which is, again, macroscopic, nothing to do with Planck scale physics. So the bottom line will be, when you take these two elements and consider light fermions near the horizon, because of the blue shifting that takes place there, the fermions can be treated as massless. And this generates a coupling through the anomaly of this four-form field to this scalar degree of freedom, and implies, in fact, an activation of torsion in that region, and lambda effective becomes space-dependent and dynamical. so it can change at the black hole horizon. And this is how it connects back to the old Schwarzschild solution and the Gravistar idea. All right, so it's a bit technical. I'll run through this. Please ask questions at the end. We really can't go through all the derivations, but just the statement of the bare facts is that it's known for a long time that the trace of the energy momentum tensor of a massless or conformal invariant field does not remain zero. It's zero classically, but does not remain zero when quantum effects are taken into account. And that leads to the trace or conformal anomaly in the stress tensor expectation value, which takes this form. So E is the this combination of Riemann and Ricci tensors, which is the Euler-Gauss-Bonnet invariant, or the Euler class, according to mathematical language. And C squared is the square of the Weil tensor. So those two things appear here, and also can appear any kind of couplings to other massless degrees of freedom, like photons or gluons in QCD. But I won't discuss these terms. We're going to concentrate mostly on the gravitational effects. And A and B are known for free fields in terms of the number of scalars, fermions, and vectors. So intrinsically, this is a non-local effect. I mean, the stress tensor trace is local, but if you try to derive this from an effect of action, you quickly find that you cannot write a local effect of action whose variation gives you this trace. So that's another discussion, but I'm just going to quote the result that you can represent this non-local effect through a local covariant action at the price of introducing another field here called phi. And then it's a relatively simple effect of action, and with a kinetic term for phi, note, and a coupling to the total anomaly. This is the script A. So this is the effect of action. I won't derive it for you, but take my word for it. And this leads to a new dynamical scalar, which I call the conformalon, just to keep it straight on what people call a dilaton in string theory, and the appearance of this order operator, so that notice this is quadratic in phi, this is linear in phi, so the equation of motion for phi is linear with the anomaly as its source. And this equation can easily be solved in certain backgrounds, which I'm going to do in a moment. And then put it back, and I won't write the stress tensor, but you can obviously derive a stress tensor from this, which is, it's a covariant action, so it's a conserved stress tensor, so you can work it out, would fill a page. It's in the papers. I won't reproduce it here. The important thing is that
we'll need to move a little quickly.
Yeah. Okay. Oh, we're almost out. Okay. All right. So I'm not going to go through the details of this, and you can ask questions later. I don't know where, I'll try to get to one of these slides where I can end, and then Evan can pick it up. So anyway, this is quantum vacuum polarization effects in terms of the scale of field, and describes non-local quantum correlations on null horizons. And you can solve this equation for the Schwarzschild background, for example. It looks like this in terms of elementary functions. There's a log, there's in principle a divergence at the horizon. That's important because when you work out the stress tensor, it also diverges at the horizon. The important thing here for this audience, I think, to emphasize is that this happens for any m, no matter how large, no matter how small the local curvature. This is a non-local effect. It's not dependent on simply the local curvature. You can trace it back to the fact that you have this extreme blue shifting on the horizon and the conformal behavior of the stress tensor. So it's a large effect on geometry in the near horizon region, in principle. Okay, so I guess I'm not going to have time to go through this, but here's the basic relations for a four-form field strength. And basically, it looks just like Maxwell's theory, where for a two-form, we usually start with a vector for the electromagnetic potential, which can be written as a one-form. Here it's a three-form. The curl of this thing is a four-form. Here's the action for it. If you have no sources, then the current is zero. Then you just get that this quantity, this scalar, is a constant. And then if you compute the stress tensor, you find it's exactly equal to a cosmological term with this normalization. So the constant is set by classical boundary conditions, and it actually minimizes in flat space, so you have no fine-tuning issue. Okay, the coupling kappa is still arbitrary. So I'll skip over this, and this is kind of the last point is that this, you remember in the anomaly, there is this topological total derivative term, the Euler-Gauss-Bonnet term, but this already is the is the dual of an exact three form, and that is the Chern-Simons three form. So this is given in terms of the affine spin connection, which is independent of the metric in general. So F can be this F that you have sitting at hand for you in any geometry. It can be identified with the F of the vacuum energy, and then A is independent of the metric and can be varied independently, and you will get a Maxwell equation. Okay, once you have a Maxwell equation with this three current, which is described here, that means F can change, and therefore the vacuum energy can change, just as phi does. It depends on the derivative of phi near the horizon within a thin world tube boundary layer. So this is the basic physics, and this, of course, depends on the fermions. When you have massless fermions, then the spin connection of the fermions is going to generate this term. So it's the anomaly term of the fermions that's important in generating this as you get close to the horizon. So I think I'm going to stop here and turn it over to Evan, because he's now going to describe how we are looking at these equations that you get in the boundary layer. Okay, so I should stop share and turn it over to Evan.
Excellent, thank you. All right, yeah, Evan, go ahead and screen share, and then you can take it away.
Perfect. Current slide. Okay, yeah, thanks, Emil, for that portion of the talk. I'm going to be talking now about some work that Emil and I have been doing over the course of the last year on the boundary layer of this gravitational condensate star, and exploring the boundary layer in this effective theory of gravity that Emil just introduced for us. So I'm going to start out by showing how we rescale the full action. So all these different terms, our conformalon, our four-form gauge field, the coupling between those two, how we rescale this full action and create what we call the boundary layer effective action that sort of describes the dynamics at the boundary layer. Then I'm going to talk about how we can sort of approximate these boundary layer dynamics using what we call ansatz functions. So it's an estimation, it's an approximation of a solution to these variational equations from the boundary layer action. We're going to analyze those ansatz results, and then finally I'll talk towards the steps we're taking towards a full numerical solution. Okay, so before we can rescale our action into our boundary layer effective action, we need to talk about what length scales we're dealing with at this boundary layer. And so there are two length scales that are particularly important. The first is on the order of 10 to the minus 5 centimeters. We're calling this big L sub f. And this is the length scale at which the lightest fermion is blue shifted to the point where we can treat it as massless. I don't think Emil had quite the time to really explain this, but it's this fermions becoming massless, which is what turns on our three current source for the four-form gauge field. So remember, we have our four-form gauge field, which is equal to 0 outside of the gravistar. It becomes positive inside the gravistar, and this three current is what turns that on, and that only can occur when we have these massless fermions. So anywhere within this scale, J becomes non-zero, our F tilde term, that's our four-form gauge field, can become dynamic. And something to point out is that this length scale does not correlate exactly to the radial coordinate scale, and that's because our metric functions are so small at this boundary layer. So if you look at this equation, delta S is our physical length scale, that's the 10 to the minus 5, and it's calculated from the coordinate length scales, in this case would be delta R. So if H is very small, then 1 over red H is very large, so delta S is going to be much larger than our coordinate scales. The second length scale to concern ourselves with is this L, and this is the length at which the conformal anomaly becomes relevant. It's much smaller than big L sub f, around 10 to the minus 15 centimeters, so 10 to the minus 14 centimeters. And so this is for a solar mass gravistar. And so this is about the thickness of a nucleus. So it's very small. At this scale, the conformal anomaly becomes very relevant. And this means the 3 current becomes very large. F tilde is going to change drastically. And this corresponds to radial coordinates on the Planck length. So once again, the Planck length is much smaller than this physical scale. But this will be the scale that the mathematics handles. And this little l is going to introduce a dimensionless parameter epsilon, which is the Planck length divided by the Schwarzschild radius, and that's on the order of 10 to the minus 40. And then we have just here a little graph for you guys to keep everything straight. This is our boundary layer. This sort of gray area is the region where we have massless fermions. And then this red region in the middle is where we have the conformal anomaly becoming highly relevant. Okay, so now that we've got an idea as to what our length scales are, let's remind ourselves what all the different terms in the actions that we have. So this is the full action written out that Emil just discussed. We have an Einstein-Hilbert term here. It's given by this. Then we have a term for our 4-form gauge field given by this in terms of this kappa parameter. We have a term for our conformalon. This handles the conformal anomaly in terms of a phi conformalon field. And then we have an interaction term due to torsion between the conformalon field and the 4-form gauge field. So in doing this, we've introduced a new parameter A prime. So if A, this was on one of Emil's slides, is related to the number of scalar, fermion, and vector fields, A sub F is the number of fermion fields. And so A prime is A with all the fermion fields taken out. And that shows up here in the anomaly action. And then A prime that's the anomaly term again with the fermions taken out. There is one other complication here, and that's at the boundary layer, this kappa term that shows up in the 4-form gauge field action becomes scale dependent. And so this scale dependence is very difficult to work with, and so we can remove it by adding a second conformalon field psi, and it is described by this action. So an action very similar to the conformalon for our phi action, and then it also has an interaction term with F tilde, and that's why phi and tube psi show up in this interaction term. Okay, so now that we've reminded ourselves of what the full action is, sort of brought that all together, let's talk about how we can use boundary layer theory to deal with it. So we cannot solve this full action directly. There are 2 reasons for that. The first is the scale of the boundary layer. Remember, gravastars we're expecting to be on the order of kilometers in size, and then our boundary layer is expected to be on the order of the radius of a nucleus. So if you were to try to numerically solve this action, you'd have to have such a fine gridding at it'd just be computationally impossible. The other issue is this action, a slide back, is very complicated. So thankfully, we can use boundary layer to solve both of these problems at once. In boundary layer theory, solve the equations of motion that come from this action in 2 parts. First, we'll have the exterior solution. So that's solving the equations of motion from this action everywhere outside of the boundary layer. So in this sense, we can neglect the terms that are not relevant outside of the boundary layer. And then we have an interior solution. So we go inside the boundary layer, neglect the terms that are not relevant inside the boundary layer, solve them, and then we match the 2 solutions on both sides. Okay, so in order to do this, we need to rescale the action at the boundary layer. So remember, boundary layer, where we can look at these 2 graphs to say we have very small metric functions at the boundary layer. That's corresponding to 1 here, where the red circle's around that. And then we have very small coordinates. So this red line here, remember, was on the order of epsilon. So it's very small. So R is going to be very small, or differences in R are going to be very small at the boundary layer, and our metric functions are going to be very small at the boundary layer. And specifically, they're going to go proportional to epsilon. So we want to take this epsilon dependence out of them. So we can rescale the radial coordinate and introduce a new x coordinate defined like this. So if R is on, differences R are on the order of epsilon, because x is multiplied by epsilon, x will be on the order of 1, which is exactly what we want. And we can also rescale our metric functions. So again, if f is on the order of epsilon, this script f will be on the order of 1. We've sort of taken the epsilon dependence out. Once we've done this, we want to rewrite the full action in terms of epsilon. And then we will only take first order terms in epsilon, because even though we are at like very small scales here, epsilon squared is still much smaller than the scales we want to worry with. So we'll just take first order terms in epsilon. And then this will give us an effect, our boundary layer effective action. And then we can minimize that to solve the variational equations from that. Okay, so just to give you guys a quick example as to how we rescale this action, we'll take the Einstein-Hilbert term. This is the classical gravity term in our action, and show how we rescale it at the boundary layer. So the Einstein-Hilbert term is given here on the left in terms of the metric g, the determinant of the metric g, and the Ricci scalar r. So we can rewrite this in terms of our metric functions f and h like this. And that's what's the term on the right is. This is after an integration by parts. So we can rewrite it as this. Then we rescale our functions f and h and our dr. So we get put in the explicit epsilon dependence, and now everything here should be on order 1. We can simplify, make some cancellations, and so we get an epsilon term multiplying this entire integral, and then terms of order 1, and then terms of order epsilon and higher. We neglect those terms of order epsilon and higher, and we get this. So this factor that's multiplying our integral will be the same for, will exist in all of the different actions that we rescale. So it won't show up later. It's just an overall scale that can be brought out. And so we have a much simpler function to deal with. And everything's on order 1 at the boundary layer. So like I said, we rescaled all the terms in the action, and we get something like this. You can see we have the Einstein-Hilbert action as the first term, just what we had on the previous slide without that leading term that was brought out. We have a term for our four-form gauge field. We've written it in terms of this W field, which is related to a rescaled four-form gauge field like this, as f tilde is red h over f dw dx. And so you can see the f tilde squared here pretty easily. We have an interaction term. This is our interaction term between the conformalon fields and the four-form gauge field. We have an anomaly term. For the phi field, we have a second anomaly term for the psi field, and then we have this beta term is the linear portion of the phi anomaly term. We've introduced these parameters alpha and beta. They're related to A prime and B. That's the number of scalar vector and fermion fields. And then we've introduced this gamma term that's related to the kappa, the kappa term of the four-form gauge field action. Something I'd like to point out is that this these conformalon terms all have second order in the derivative of the conformalon field. So we have either a D'Alembert here, or we have just a plain derivative squared. And this is important because dx will go as epsilon. So once we get to this boundary layer, we'll get 1 over epsilon squared terms appearing in these conformalon terms. And that's what makes them, that's where you see this becoming important at the boundary layer. Far away from the boundary layer, these derivatives are small. And so these terms aren't important, but as we get to the boundary layer, these derivatives become very large. And that's what makes these terms of the action important. The last thing I'll mention is that we'll be taking bounds on these integrals from something called x minus to x plus. These, that's what we'll call the integral bounds, is x minus x plus. And the scale of those bounds will correspond to that LF scale that I mentioned on my first slide, which is the length scale at which the length scale at which massless fermions become important. So the blue shifting becomes strong enough that we get massless fermions. Okay, so now that we have our action, let's talk about the boundary layer that solutions to the variational equations of this action will need to satisfy. So, every solution will need to satisfy certain boundary conditions at x minus and x plus. The conditions will either be on the function's value or the value of the function's derivatives. Whether or not the conditions will be on the value or the value of the derivatives, or both, is determined from the variational principle. And then what the actual condition will be is determined by matching it from the exterior solution. So say we have our metric function f. We'll determine if it has boundary conditions on f of x or f prime of x, or both, from the variational principle. But then what exactly those conditions will come from matching from the exterior solution. And by exterior solution, I mean the solution outside of the boundary layer. So let's do an example now with that metric function f. The variational principle tells us that there should be conditions on both the value and its derivatives at both boundaries. So we need values on f and f prime at both boundaries. The Gravistar interior solution, and so this is where I apologize, the interior and exterior is getting a bit mixed up. By interior solution here, I mean interior to the Gravistar, so less than the Schwarzschild radius. The metric functions given by this, Emil brought this up in his talk very nicely. We can rescale it in terms of this epsilon parameter, simplify things down in terms of this script f parameter, and we get this as the form that script f will take as we get towards the boundary layer. So f will go as minus x over 2 at the boundary layer, and then we take that and put it right into our boundary conditions. So we say that f at x minus, that's the left boundary, needs to go as minus x minus over 2, and then its derivative goes as minus 1/2. We can do the same thing for the exterior solution. In this case, exterior, I mean exterior to the Gravistar, not just exterior to the boundary layer. We get that f goes as x, and so we get the respective boundary conditions from that. Once we've done all this, we find that we need 4 conditions on our f, phi, and psi fields. So both the value and the derivatives need to be pinned down at the boundaries. And then only 2 conditions on h and f tilde. And so just the values need to be pinned down at the boundaries. And these are what those conditions are. You'll notice that for the metric functions, they're given exact numbers. However, for these conformalon fields, they're given in terms of these integration constants. And those integration constants are the same integration constants that show up in the macroscopic solutions that Emil went over. Okay, so now we have everything set up to go and solve for the variational equations. We won't actually solve the variational equations. What we're going to do is numerically minimize this action, but it's the same concept, or the same result. But rather than jumping in and solving everything right away, what we're going to do is introduce an approximate solution first that we're calling an ansatz. So we want to create an approximate solution without fully solving, and there are 2 benefits of this. The first benefit is that it's going to give insight into the behavior of the full solution. So, there are difficulties that come in with just jumping right into the full solution. Let's get some insight into how everything works, and then, move on. You move on to the full solution after that. The second benefit is that the full numerical solution will need an initial seed for the minimization algorithm that we use. And so the ansatz will help us generate that initial seed. So how do we create this ansatz? We'll create trial functions for our 5 free fields, and we'll call these trial functions the ansatz. And these will be in terms of 2 free parameters, eta and lambda. So these free parameters will then be varied to find the minimum of our action. Yeah, so the ansatz functions will satisfy the boundary conditions, and we, like I said, we extremize our action with respect to eta and lambda. Okay, so let's go into an example as to how we would create this ansatz. So, or walk through the steps, and then there'll be an example after this. So we need to create 2 trial functions that match the left or right boundary condition. So one trial function will match the left boundary condition, another trial function will match the right boundary condition. These trial functions will depend on the free parameter eta, which regularizes the cusp in the metric. So if you remember back to Emil's portion of the talk, we had I mentioned this in my portion of the talk, we have our metric functions f and h that go to 0 at the Schwarzschild radius, at the Gravistar boundary layer. This eta allows that to not happen. So if eta equals 0, the functions will go to 0. So for the class, like they do in the classical solution, without these conformal fields added, and the 4-form gauge field added. However, this eta allows that in our new effective action, that if that's preferred, that won't happen. And then we add, and then we combine the 2 trial functions. Well, they can be turned on and off in each region with the heavy side, with this smooth version of the heavy side function, which also depends on lambda. So in this case, lambda will control how much these 2 trial functions mix with each other. We add the functions together to create the ansatz, and then that's how it's created. So here's an example that hopefully helps clear some of these issues up. So again, taking the f metric function with these specific boundary conditions, we want to create 2 functions that match these boundary conditions. So on the left, we pick this function, which matches them. And on the right, we picked this function, which also matches the boundary conditions. The full ansatz will satisfy, because these two functions match the boundary conditions, the full ansatz will also satisfy the boundary conditions as long as we're looking at the boundary to be much greater than 1 and eta and lambda don't become ridiculously large or ridiculously small. Like I said, so the full action or the full ansatz combines these two functions like this, and they're smoothed with the heaviside theta functions. And now this is some plots showing how this is done. So the blue curve is that F minus, which matches the boundary condition on the left. The orange curve matches the boundary condition on the right. So they're drawn out here in the upper left. Then we add the smoothed heaviside theta functions, which you can see turns them on and off in each region, and then we add them together. We got our ansatz function for f of x. So I chose eta and lambda to be 1 in both of these, but varying eta and lambda would change how this ansatz looks. Okay, so we can create ansatzes for all 5 of our functions in our effective action, and then we can numerically minimize that action with respect to eta and lambda. The exact values of eta and lambda that we get will depend on our choices of parameters, but for this, we simply chose alpha to be 1, beta to be 0, gamma to be 1, and epsilon to be 10 to the minus 4. Of course, 10 to the minus 4 is not particularly physical. However, it's numerically much easier to work with than 10 to the minus 40 would be. And because we're just trying to get a sense of what goes on, it makes sense to use a larger value of epsilon. And for these specific values, we get eta on the order of 3 and lambda on the order of 0.7. And here we have a graph showing this. So the surface is the value of the action at various values of eta and lambda. Where it's blue and green, the action is higher, but in the red area, that's where the action is lower. And as you can see, this is a proper minimum. Okay, now that we have our ansatz solution, let's look at some results. There are two things we can look at. The first thing from the ansatz is we can see a competition between the classical terms and the quantum terms pushing our ansatz functions in different directions. The classical terms want to push eta towards 0 and lambda towards infinity, and the quantum terms want to do the opposite, pushing eta towards infinity and lambda towards 0. And again, this is exactly what we would expect, because if you remember, the classical Gravistar solution had our metric functions hitting 0 at the Schwarzschild radius. That corresponds to eta equals 0. And they had a sharp switched over between the two functions. There's no mixing between the functions, and that corresponds to lambda going to infinity. And the quantum terms want to push that in the opposite direction. This will also affect the behavior of the surface gravity kappa. And Emil introduced the surface gravity kappa, and I'll show in a few slides how this behavior is affected. First, we can see this competition between the classical and quantum terms. So in the upper left graph, we have the Einstein-Hilbert action plotted with different values of eta. And as you can see, eta is pushed towards 0 by the Einstein-Hilbert action. However, on the right, we have the anomaly terms that push eta towards infinity. This is what I mean by this competition. And they find some mutual ground in the middle. And then the same thing, but in opposite directions with lambda for in the bottom here. We have the Einstein-Hilbert action pushing lambda towards infinity, and we have the quantum anomaly actions pushing lambda towards 0. Okay, now how is the surface gravity affected? If you remember, for the classical Gravistar, that was without the conformal anomaly, without the four-form gauge field added, without this boundary layer rescaling. The surface gravity was simply a step function at the Schwarzschild radius. So it went from -½ to 1/2. It's just stepped right up, and that's in units of 1 over the Schwarzschild radius. And here we can see that it's been smoothed out now in this ansatz. So it's smoothed out, but it's still quite steep. Remember, x is on the order of that L. So 1x is more or less on the order of the size of a nucleus. So it's still quite steep, but it's not sharp anymore. And the same thing happens with the derivative of the surface gravity. Remember, the derivative of a step function is a delta function. So it was a delta function, and it's been smoothed out slightly. But again, very, very steep. These units are in 1 over L squared. And the derivative of the surface gravity is important because it relates to the Riemann tensor like this. Okay, so now that we have our ansatz, our approximate solution, I can start talking about the steps we've been taking towards a full numerical solution. So it's very difficult to numerically minimize a functional that's a function of functions, which is what we have for our action. And so what we want to do is we want to approximate this action functional as a discretized function. So in terms of values, not in terms of functions. To do this, we split up our the area we're integrating over into finite number of points. We'll label them xn. So x0 might be that x minus our left boundary all the way to say x 2000 if we're taking 2000 points, which would be x plus. Each function will then be discretized into a variety of discretized variables. Again, if we're taking 2000 points, that means we have 2000 different variables for each function. So that's 10,000 in total. And each discretized variable corresponds to the value of a function at one of those discretized points. And then we replace the derivatives in our function with finite differences. And so in this way, we can rewrite our action functional as a function of all of these discretized variables. From there, we employ the Newton-Raphson extremization algorithm to minimize or extremize our action functional, or what was an action functional is now just an action function. And in order to enforce the boundary conditions, we have to be careful about how we choose dynamic and static points. So if we just allowed all of these variables to vary, there's no guarantee that our solution would satisfy the boundary conditions. In fact, we probably wouldn't get a solution because we're talking about, high order differential equations with no boundary conditions. So we need to enforce the boundary conditions in order to get a solution. And what we do is we pin down the value of our discretized variables at each boundary based on, in order to enforce those boundary conditions. So if it's just a boundary condition on the value, we just pin down one static point on the boundary. If it's a condition on both the value and the derivative, we pin down two in order to enforce both the value and the derivative. Something else we can do finally is once we get these solutions, we can compare our results with the expected Euler-Lagrange equations from varying our effective action functional and make sure that our solutions match what we would expect. We have some preliminary results here. So what I've done is I've kept the metric functions fixed. So f and h are fixed, and I varied the conformalon and the four-form fields. And the results are shown on the right here. So in the top right, we have in orange, the ansatz for the phi conformalon field. And in red, we have the result of our Newton-Raphson algorithm. And then the same thing for the psi ansatz. So purple is the psi ansatz, and then blue is the result. In the bottom here, we have the four-form gauge field, in, again, orange being the ansatz, red being the result. And we've gone and checked, and these solutions match the expected equations of motion. And so the next step that we're currently working on is finding similar solutions for the metric function so we can get that full solution for the Gravitational boundary layer. So just a quick summary. We have the Gravitational boundary layer has no event horizon, but there's still a lot of eventful things happening here. We have extreme blue shifting, which leads to massless fermions. This means we have this non-local conformal leads to massless fermions. We also have a very important contribution to the stress energy tensor from the non-local conformal anomaly. We have a non-zero value of our 3 current J. F tilde becomes dynamic. What we've derived the boundary layer effective action that describes all of this behavior. We introduced some ansatzes to get a sense as to what's going on, and full numerical results will improve the insights we've gotten from our ansatz. So we have a full summary slide here, but I think I will just let you guys read this as we stop and take questions. Oh, and I stopped my share. I'm sorry about that. Put that back up.
All right, excellent job. That was really interesting. Thank you so much. All right, open it up to questions. Yeah, go ahead, Andrew.
Thank you very much. So anything about this policy of this arrangement? And there's a related question, which is what happens with merging of two black holes and the gravitational waves which emerge?
Yeah, so there was a little bit of feedback, so I'm not sure if I fully got your question, but it seemed like you were asking about merging of gravitational waves, or merging of black holes and respective gravitational waves.
Yes, that was the second half. The first half was do you have any idea whether your solution is stable? It's two related questions.
Okay, yeah. So to take the second question, it certainly would be interesting to look at the merging of two gravastars and see if the gravitational wave would the gravitational wave signature would be different from that. I certainly haven't done any work as to what that actually would look like, or if that would actually be possible, if we could do it with current LIGO, if it would take next generation LIGO. I know Emil has had some conversations with people about this. Maybe he can speak more to that. In terms of stability, do you mean stable from further collapse into a singularity? Do you mean, is that?
Well, if you perturbed your horizon a little bit, kind of what happens? Does it try and go back to where it was or not?
Sure, yeah. We haven't done full work on that I'm aware of. I know we've talked about that being an interesting next step. I don't know, Emil, if you have something to add to that.
Yeah. So the indication of stability is the positivity of the surface tension, that equation that I wrote, that the change in the energy increases if you change the area. So if you put wiggles on it on the horizon, because the surface tension is positive, that will cost you energy. So that indicates that it should be stable. However, to really prove that, you have to have this solution and then look at small perturbations around it. And we're just actually finding the solution now. So the small perturbation analysis would have to be done next for stability to prove it. That's the only way to fully answer that question. Of course, with this effective action, you can ask many more questions besides static solutions. You have, you can solve equations of motion in particular for time-dependent things, but obviously that's much more complicated and down the road.
All right, great. Any more questions?
Yes.
Go ahead.
I was just wondering if you had a chance to look at how eta and lambda vary with the other 5 parameters. Like if you change epsilon or alpha or beta.
Yeah, we've looked at that some, changing gamma specifically, because gamma is in terms of this kappa field, and it's not exactly clear what kappa is equal to. It changed, we had a graph about this. It changes, on the order of 0.1 or 0.2 to eta or lambda, bringing gamma from 1 to 0.1. So there is change, but it's not that drastic on the order of, it's not that drastic as long as your changes are on the order of, order of 10 or so. I'm sure if you brought it to 10,000, it would change rather drastically, but changes on the order of 1 order of magnitude don't really change the values of beta and lambda too much.
Okay.
Good question. Thank you.
All right, Joaquin.
Yeah, I don't really know if this question makes a lot of sense, but I mean, when you have the solution for this approximate solution for the phi's, you can in principle calculate the stress energy tensor that comes from these fields. And just when I saw this talk now, I remember that there was some papers discussing the equation of state of the matter on the boundary layer. So I was wondering if with what you've done so far, you can look into like basically the equation of state of the matter on the boundary layer. Is that something that makes sense and that you can do?
Yeah, it's interesting. So part of what might make that difficult is the boundary layer itself is not isotropic in the sense that our P radial is different from P perp. And I feel that the equation of state usually assumes isotropic matter. I might be wrong about that. But that's interesting. It's not something that we've thought about. But yeah, certainly interesting. I don't know. Yeah.
Thank you.
All right, great. Well, since we've reached the top of the hour, let's go ahead and thank our speakers again. And I'll just remind you guys that we will be back here again in 1 month for our next talk. All right, thank you, everybody.
Yeah, thank you all.
Thank you.